Okay, let's talk about some of the basic mathematical formalism or mathematical methods for the circular waveguide. So first things first, I've drawn kind of like this hollow tube here. It's a little difficult to, I'm not the best artist in the world, but it's just this hollow circular tube with a radius of a, and then the z direction is coming out of the page here, which I've drawn in green. And that is the longitudinal axis down the waveguide. So obviously there's some cylindrical symmetry for this waveguide, so it makes perfect sense to try and express this problem in cylindrical coordinates. So I'm going to imagine some arbitrary point here inside the waveguide along some cross section, and it is going to have a radius of rho, so that is a variable radius, and then it will have some angle phi here relative to the x-axis. Okay, so you can imagine here is my x-hat, and then my y-axis goes up that way. But I'm going to convert everything into cylindrical or polar coordinates. So rather than saying my electric field has x, y, and z components, I'm going to write it as the following. My electric field has a rho component, E sub rho, plus a phi hat, E sub phi, plus z hat, E sub z. So these are cylindrical coordinates. I'm not really a fan of the use of rho because rho tends to get confused with charge density, but it is very common in mathematics and physics to use this as the radial coordinate in cylindrical coordinates anyway. So we're just going to kind of go with it. And of course, we're going to have the same thing. My H field will have a rho hat, H sub rho, plus a phi hat, H sub phi, plus a z hat, H sub z. And depending on your polarization, we're still going to have that same TE or TM polarization. So TE polarization will imply E sub z is equal to 0. And then if I said TM polarization, that would imply H sub z equal to 0. We're also going to assume that same z dependence of e to the minus j beta z. So you can do that thing where you, instead of writing capital E of all three variables, we can write something like E is equal to rho hat E little e sub rho plus phi hat E sub phi. And if we're in transverse electric, this z bit will go away, and then I would write e to the minus j beta z. So don't confuse these little e's with this Euler's constant here. These are scalar functions representing the electric field, and this is the Euler's constant for the complex exponential. Now, we also showed that in any generic sense, if we assume TE polarization, we got a Helmholtz equation on my little h sub z. So del squared h sub z plus k squared h sub z is equal to 0. And that worked out great, and nothing really changed because we still assumed the polarizations here. The only thing we have to modify is this del squared has to be expressed in cylindrical coordinates. So we write that out. This is basically a table lookup, but it looks like the following. Partial squared respect to rho squared plus 1 over rho, partial with respect to rho, plus 1 over rho squared, partial squared with respect to phi squared. And if I do the whole thing, I'll get h sub z plus k sub c squared, h sub z. And where, of course, k sub c squared was going to be k naught squared minus my beta squared. Okay, so nothing's really changed. This Helmholtz equation still has to be satisfied. We're going to do it in cylindrical polar coordinates rather than rectangular coordinates. And that's going to have some interesting mathematical consequences. And we're also going to do that same idea where this is our anchor point, where if I can calculate this, I will then be able to rederive all of the other, or not rederive, but then summarily calculate all of the other field components. So that just fell out of Maxwell's equations by doing the curls and then some substitutions. So we're just going to skip to the end because it's the exact same idea. You just do it in polar coordinates and you get the following. E sub rho is equal to minus j omega mu naught divided by k sub c squared rho. So that's very important. Partial h sub z with respect to phi. And then my E sub phi becomes plus j omega mu naught divided by k sub c squared partial h sub z with respect to rho. So you notice there's a rho here, but there is not a rho over here. And that's just one of the consequences of using polar coordinates here rather than rectangular. And then you do a similar argument. H sub rho is equal to minus j beta over k sub c squared partial h sub z over with respect to rho, and then my h sub phi is equal to minus j beta over k sub c squared rho. And then there will be a partial h sub z with respect to phi. Okay, so we're not going to bother with the derivation. It's the exact same argument we did last time. You just have to do it in polar coordinates rather than rectangular. And most of this stuff looks very similar, but we have these phis and rhos now instead of x and y. And this rho here popped out that is not here, and it's over here but not here, that you have to keep track of. And that's just one of the consequences of doing things in polar coordinates. Okay, so from here, we will then calculate h sub z by solving this giant partial differential equation. And once we have this term, we can then rederive all the other terms accordingly. Okay, so that's the basic mathematical formalism that we will be exploiting to solve the circular waveguide problems in both TE and TM polarization. All right, so I wrote out the TE versions here, and of course if I want to do TM, I replace this with an E sub z rather than H, and then there's a similar derivation here accordingly, which you can see in your book. You don't have to write it down here. It's all summarized for you.